Yeah. Hello? Uh, can hear me? Just please let me know if I'm audible. Okay. Thank you, Sariha. Yeah, good afternoon. We'll wait for a couple of minutes and then we'll start. So did you try the problem that I asked for? Like the CSIR net February 2022, this complex analysis? Okay. So basically today we'll discuss um, like this complex analysis problems. Okay, Manmohan. And since the number of questions were less, only I guess 8 questions were there. So I collected a bunch of more problems, like uh, more, I guess 3 or 4 problems I have collected, and that was mostly on the identity theorem, maximum modulus principle, Liebel's theorem, those kind of application. And this kind of question is usually like frequently asked in CSIR net. So I hope you will be benefited with those questions. Yeah, so we can wait just 1 minute and then we can start the session. Okay, so I guess it's time to start now. So hello and welcome again. So let's see. As I told that we'll be discussing the problem on complex analysis, and these problems were asked in February 2022. And yeah, so and you will see that the problems are fairly simple. So if you are comfortable with basic complex analysis and basic results, then easily you can solve at least 60 to 70% problems in complex analysis. At least that's for sure. So let's see. Yeah. So the first problem is very simple. So yeah. So it says that if fz be a non-constant entire function and z is equals to x plus iy, and let u and v denote its real and imaginary parts respectively, then which of the following statement is false? So it's like f of z is equals to uxy plus I vxy. Okay. So this is a simple problem. So can you tell me like which of the option is false? Yeah, B. Okay. Yeah, two. Right. Yeah, you all are right. So this is just the Cauchy-Riemann equation. So you recall that. Cauchy-Riemann equations. Yeah. So it says that uh, if u and the partial derivative of in u and v exist at some point z naught or x naught y naught, then the Cauchy-Riemann equation says that the derivative of u with respect to x is same as by, and uy is same as minus of vx. Okay, so these are the Cauchy-Riemann equations. So the first is basically the Cauchy-Riemann equation, or in short CR equation. So this is a true statement. The second says that ui equals to vx. That's not correct. It's ui equals to minus vx. So this is false. And that is what in the problem you are asked to find out. And these two are correct because if f is an analytic function, here it's the entire function, so f is a differentiable function. And if it is differentiable, then f prime at any z is same as ux plus ivx, or it is also same as ui plus I dy. Okay. So therefore, these two are also correct statements. So therefore, the false is the second one. Okay. So I guess it is clear. So it is just the application of Cauchy-Riemann equation and what is the derivative of an analytic function at some point. Okay. So let's proceed to the next problem. Yeah. Yeah. So says that D is an open unit disk. So this is B. Yeah. So let D be the open unit disk and OD be the space of all holomorphic functions on D. Okay. So this means that whatever F is in OD, so this F is analytic on D or holomorphic on D. Okay. Yeah, and now you have two sets A and B defined as defined on the 1 by n number, and then you are asked to find out which of the following statement is true. So what do you see that which of the following statement is true? Yeah, so do you have any guess? B. Okay, so let's mark it. Yeah, Chino. Yeah, right. Yeah, you both are right. So this is correct, and this is basically an easy application to the identity theorem. And what it says that it says if you have two functions f and g, and if two functions are equal on S, okay, and let's say suppose that so this on S and see, and let's say the limit point is also belongs to the in the domain, then f and g it will be same on D. D is the domain. Okay, so if limit point of S also belongs to D. Okay, so if the limit point of S belongs to D, then the two functions will be same on the domain D. Okay, so this is basically the application. This problem is an application to the identity theorem. So see, note that what is A? So A is set of all holomorphic functions on D such that f of 1 by n is equals to e to the minus n and 0 if n is odd. So if I consider S to be set of all 1 by n such that n is odd and n is bigger than equals to 2. So if you consider this set, so f is equals to 0 on S. You see that f of 1 by n equals to 0 if n is odd. And here n is odd, so f of 1 by n equals to 0. And therefore f is equals to 0 on S. Now, what is the limit point of S? 0 is the limit point of S. Okay, so 1 by n converges to 0. and 0 belongs to the open unit disk. And therefore, F, this from the identity theorem implies that F equals to 0 on D. Okay, but it says that if n is even, then it's e to the minus n. But you see that f is entirely 0 on whole of the disk. So whatever the value you will take, it is always be 0. So so therefore a is equals to the empty set. Okay. In first question, is the form derivative, second one for fz is correct. Let me see. Okay, so ux equals to vy and uy equals to, or vx equals to, probably not, I guess, uy. So I guess this will be equals to ux equals to vy. So that's vy and plus I and minus uy. Yeah, so this is basically this. So this is not correct. This is vy minus I uy. Yeah, thanks, Manmohan. This is this. This is my vy minus I uy. This. So this is just from the CR equation. So from equations. Okay. Yeah, thanks for pointing this out. Right. So I hope this is now correct. Okay. Yeah. So yeah, so therefore in this problem, uh, this is an empty set. Why? Because f is entirely 0 on whole of the disk, but it says that if n is even, then f of 1 by n equals to e to the minus n. So in particular, f of 1 by 2 is equals to e to the minus 2, which is not equals to 0. Okay. So therefore this set is empty. Now the B, that is also same. So what is B? So B is f holomorphic on D such that f of 1 by n is equals to n minus 2 by n minus 1. Okay. Again, what I'll do, I'll take s as again 1 by n such that n is in natural number. Okay, and n is bigger than equal to 2. Okay. Now you see that what is this? This I can write n by minus 2 by n minus 1. This I can write 1 minus 2 by 1 minus 1 by n. So if I write fz equals to 1 minus 2z or 1 minus z, then fz is equals to this function, and clearly, or let's write gz. So if I write gz equals to this, then it is clear that f equals to g on s. So this again from the identity theorem. So again from the identity theorem, because the limit point of s, which is 0, 0 belongs to D, and 0 is a limit point of S. Okay, and therefore from the identity theorem, we conclude that f equals to g on whole of D. Okay, and this proves that this has only one function, and what is this B? So B is equals to f for f z, which is equals to 1 minus 2z by 1 minus z. Okay, so this is B. So what is the cardinality of B? So the cardinality of B is 1. So therefore, this option A is empty and B has exactly one element is correct. So is it clear for everyone? So you will see that this identity theorem is being used a lot many times. Okay, and this is very important theorem. Usually lot of problems being asked with the identity theorem. Okay, so we'll proceed to the next problem. If any doubt, please let me know. Yeah. So let f be a rational function of a complex variable z, which is given by fz equals to z cube plus 2z minus 4 by z. Okay, and we need to find out the convergence of the Taylor series of f around z equals to 1. Okay. So what is the radius of convergence? So radius of convergence means, so the largest ball on which f is analytic. Okay. So what is the radius of convergence here? Do you have any guess? 1. So this is second. Okay. Right. Yeah, you both are right. So yeah. So this is also an easy problem. So let's see. See, there are multiple of ways to solve it. So what I did is like you can write fz equals to z square plus 2 minus 4 by z. Okay. So see, this is what? This is like, this is an analytic function, so the radius of convergence is infinity here. So this will not alter the radius of convergence. So we basically need to think about the last thing, minus 4 by z. So let's see 4 by z. So the radius of convergence of f here, so radius of convergence of the Taylor series of f will be will be same as that of g z equals to 4 by z or minus 4 by z. Okay. So now, and we need to find out the Taylor series around z equals to 1. Okay. So see, we can write 4 by z as equals to 4 by z minus 1 plus 1. And what is this? This is 4 by w plus 1. And this is what? This is nothing but 4 times. And if you recall, this is a sum of this geometric series. So this is 1 minus w plus w square minus this. And what is the radius of convergence of this? This is 1. And therefore, the radius of convergence of f, so the radius of convergence of f is equals to 1. Okay. This is one way to see. There is another way to see this problem. See, what I told, that radius of convergence means what? It is the largest ball, and we need to find out the radius of convergence at z minus 1. So it's like Taylor series with centered at 1. So the radius of convergence is the radius of the largest ball whose center is 1 and the radius, so that the function will be holomorphic. So here, or analytic. So here, if I'll see at z equals to 1, so this is my center. Okay. Now, if I take a ball, so you see that any ball of radius 1, inside this, the function is analytic. Why? Because function has something plus 4 by z. So once it crosses the 0 value, it is not analytic. Okay, once it crosses this 0, it is not analytic. And therefore, this is the largest ball on which it is analytic, because this function is analytic in this domain. So therefore, from this diagrammatic view, also you can say that the radius of convergence is equals to 1. Okay. So I hope this is clear to everyone. If any doubt, you can stop me. We will proceed to the next problem. Okay, thank you. Yeah, yes. So let gamma be the positively oriented circle Z in C such that mod Z equals to 3 by 2. So it's basically a circle of radius 3 by 2. Now we suppose that integral of gamma e to the I pi z by z minus 1 times z minus 2i square equals to 2 pi I c, then we need to find out what is the absolute value of c. So any thought about this problem? Option 4. Okay. Yeah. Yeah, you are right. So I guess, so let's see. So see, this function, we see from the Cauchy's theorem, what we know, that we'll just recall the Cauchy's theorem also here, that if f is analytic inside gamma, then this integral is 0. Okay. So this is the Cauchy integral theorem that says that if you have the domain D here and f is analytic on D and gamma be any closed curve in D, then this integral is 0. Okay, but you see that what is Z? Z is what is gamma? Gamma is the circle of radius 3 by 2. Okay, so I'll just make it the circle of radius 3 by 2. So this is okay. So this is my mod Z equals to 3 by 2. So yeah. So you see that 1 is inside this. So 1 is basically here. Z equals to 1. Or it's not here, it's basically here. Yeah. So 1 is there, and therefore the given function is not analytic. So then we have another theorem which says that if you have fz by z minus z naught, okay, on gamma, such that fz is analytic inside D or inside the region gamma, okay, and gamma is what? Gamma contains, so this here is basically z naught. Somewhere z naught is there. Then what is this value? This is equal to f at z naught. Okay, so this is what we are going to apply. So you see that if I'll take this as my f, so if I'll take fz equals to e to the I by z by z minus 2i square, then what? This is my fz. Okay, so if I take this as my fz, so what is the singularity? Singularity is 2i, where this denominator vanishes. Okay, and which is outside. So it's basically somewhere here. Okay, so this is outside. So therefore, this function is analytic. On or inside gamma. Okay, so here it's analytic. So therefore, we can apply this theorem, and hence, what is the so it's sorry, it's 1 by 2 pi I. Yeah. So therefore, this integral fz by z minus z naught dz is 2 pi I fz naught. So we need to find out what is the absolute value of fz naught. That is basically my C. Okay. So what is this? So f was fz is equals to e to the power 2 e to the power I pi z by z minus 2i square. So we need to find out the absolute value of f1. So what is f of 1? It's e to the power I pi by 1 minus 2i square. Okay. So if we'll take the absolute value, this is what? This is 1 by 1 minus 2i square. What is this? This is, and absolute value is the square of this, sorry. Yeah. So what is this? This is basically 1 by 5. Okay. So, sorry. I'm sorry. Yeah. Yes. So absolute value of 1 minus 2i is equals to square root of 5. Okay. So this says that the value of C is equals to 1 by 5. So I guess 1 by 5 was the guess. Yeah. So this is the correct answer. So this theorem is also an important theorem, and I guess a similar theorem, it says that, so please correct me if I'm wrong, it says that if you have fz by z minus z naught to the n, so now you have the z naught is a 0 of this function, or a pole of this of order n, then this is equals to, or 1 by 2 pi I is equals to, I guess, n minus 1 factorial fn z naught. Yeah, I guess 1 by, I guess. So yeah, yeah. So this is the value of this. Okay. So this, along with the earlier result, is quite an important result. Quite important results. This is the first result, and the second, as I told earlier, that integral of fz by z minus z naught equals to 2 pi I fz naught. Okay, the condition in this both theorem that fz has to be analytic inside gamma. Okay, so this problem I guess is clear to everyone. If it is not, please let me know. Yeah, because we'll now proceed to the part C. Okay, so I hope it is clear to everyone. Yeah, so we are on part C, right? So it says that for any complex valued function f, let df denote the set on which the function f satisfies the CR equations. We have already discussed the CR equation in the earlier, that if f is equals to u plus iv, then what is CR equation? It's ux equals to vy and uy equals to minus vx. So, and we need to find out, identify the functions in the options for which df equals to c. So it means that we need to identify the function for which the Cauchy-Riemann equation satisfies for all complex numbers. Okay. So recall that if a function is analytic, then the Cauchy-Riemann will be satisfying for all points. Okay. So what is your thought about this problem? So which of the options are correct? Yeah. So any thought? Okay. So it's not a difficult problem. So let's see. So yeah. So what is the first option? First option is fz equals to z by 1 plus mod z. Okay. See, since it has a mod z involved, so it's whenever you have mod z involved, it's better to write it in the r theta coordinate or in the polar coordinate. So if I write z equals to r e to the power I theta, then what is my f of r theta is equals to r e to the power I theta by 1 plus r. Okay. Now we recall that. So this is the Cauchy-Riemann equation in usual coordinate, and in r theta coordinate, Cauchy-Riemann equation. So basically f r theta is equals to u r theta plus I v r theta. And then I guess u r equals to 1 by r v theta, and I guess u theta equals to minus 1 by r, or r, I guess. Let me see. Yeah. So yeah. So this is u r equals to 1 by r v theta, and u theta equals to minus r v r. Okay. So this is basically the Cauchy-Riemann equations in polar coordinates. Okay. Yeah, you can do that. You can find out. Yeah, I was just about to tell uh, an equivalent condition. So an equivalent condition for the Cauchy-Riemann equation, or equivalent equation, I will say, Riemann equations is del f by del z bar is equals to 0. Okay, so you take the z bar derivative. For example, suppose that you have a function. So just since this might be new, so let's say if you have a function fz equals to z bar plus e to the z. So what we will do in order to see if it satisfies the Cauchy-Riemann equation, we'll find out del f by del z bar. Okay, and what is this? This is z. So this is not 0. So therefore, this does not satisfy the Cauchy-Riemann equation. Okay. Instead of, let's say we have z, if this, then we'll say this is 0, and it satisfies the Cauchy-Riemann equation. Okay. So this is the same thing. So as suggested by Sariha, so we can also find out. So we can write fz equals to z by 1 plus z bar square root, and we can find out del f by del z bar to see when it is 0. If it is 0 for every complex number, then this is a correct option. If it is not 0 for some complex number z, then this is not a correct option. Okay. So let's do by both method here. Okay. So let's start with firstly by r theta. So what is my f? F of r theta equals to r e to the I theta. So r cosine theta plus I sine theta by 1 plus r. Okay, so this is my, so u is equals to r by 1 plus r times cosine theta, and v is r by 1 plus r sine theta. Okay, so what is my ur? Ur will be, so this is basically, so what is ur? This is, if I can just write this as 1 plus 1 by r, or 1 by 1 plus r plus 1, right? So this, I can write 1 minus 1 by 1 plus r, fine. Yeah. So this derivative will be 1 by 1 plus r square times cosine theta. And if you take v theta, this is equals to r by 1 plus r times cosine theta. And we need to, we see what is the condition. It says that ur equals to 1 by r v theta. But ur is this, and 1 by r v theta is this, which is not same. They are not same for all r and theta. Okay. For example, they are not same if r is equals to 2, or even for r equals to 1, they are not same. And therefore, this does not satisfy the Cauchy-Riemann equation for all r, all z. Okay. Yeah. Now let's see the another method, like del f by del z bar. Okay. Equals to 0 or not. So what is the function? So fz equals to z by 1 plus square root z bar. Okay, so we just need to find out what is del f by del z bar. This is z by 1 plus square root z bar, and this is minus 1, so this is square, and then I'll have to do a minus, and then I have to take the derivative of this, which is 1 by 2, and I guess square root z. Okay, and then some z will be coming, I guess. Yeah, I guess this is right. Yeah, or maybe not. This is right. Yeah, but this is obviously not 0 for all z. Okay, this is 0 for z equals to 0. So this is not 0 for all z. And this also says that this does not satisfy the CR equation on whole of R. You just check it. So you can just check it if the, okay, right. So this is false. So this is where it went. Oh, sorry. Okay. Okay, so it went after this. So let me add after this. Yeah. Now it will be after this, right? Yeah. So now we'll go for the option 2. So what is option 2? So it's cosine alpha x minus sine alpha y. So that we can, so u is my uxy is equals to cosine alpha x minus sine alpha y, and vxy is equals to, I guess, sine alpha x minus cosine, sine plus cosine. Okay. So it's sine alpha x plus cosine alpha y. Okay, so if f is analytic, then the z bar derivative is 0, but not the converse. That is, the derivative is 0, then we cannot say that f is analytic. Yeah, see, what I am saying that this is just an equivalent condition. You are right. See, this Cauchy-Riemann equation, this is just an equivalent. This is same as del f by del z bar equals to 0. This is just Cauchy-Riemann equation. You are right that if f is analytic, then the z bar derivative equals to 0 does not imply the uh, analyticity. That is same as if f satisfies CR equations, this does not imply f is analytic. Okay, this is basically, this is same as f satisfies CR equation means that del f by del z bar equals to 0. Okay, or whatever the two condition you saw, that ux equals to by, uy equals to minus vx, and similarly the r theta. Okay, so f satisfies the CR equation is same as the del f by del z bar equals to 0. But satisfying the CR equation does not guarantee the analyticity. You are right. We can only say that this part, that if f is analytic, then f satisfies the CR equation. This is right, this is false. Okay, and you will see an example in this problem only. Okay, so yeah, so let's work out ux. What is ux? Ux is sine alpha x minus sine alpha x minus cosine alpha y. Alpha will be there. And what is vy? So vy is alpha sine alpha cosine alpha x minus alpha sine alpha y, and they are not same for every value. So of course this is also not a correct option. So this is also false. So this is not true. This is not true. Let's see the fourth one that looks less complicated. So here u is my uxy. Right. So if ux vy vx vy exist, and if the partial derivative are continuous, okay, and if it satisfies the CR equation, that is same as the del z bar derivative is 0, then you can say that f is analytic. You are right. That f satisfies the CR equation and the partial derivatives are continuous, then we say that f is analytic. So that is right. Whatever you wrote, Aviru, that's right. So in this, uxy is equals to x square and vxy is equals to y square. And clearly, this is not analytic. This does not satisfy the Cauchy-Riemann equation for all the complex number, because ux is 2x and vy is 2y. So they are not same. Okay, so this option is also false. So apparently this option should right, but let's check that. Okay. So fz equals to e to the minus 1 by z to the power 4, and you will see that this function satisfies the CR equation, but this is not analytic. Indeed, this is not continuous. Okay, at z equals to 0. So let's see. So the function is fz equals to e to the power minus 1 by z to the power 4. Okay, and 0. Here this is z not equals to 0, and this is z equals to 0. Okay. So see, first of all, let's check if it is continuous. So you see that if I take z equals to, so what I'm claiming, that limit z tends to 0, f of z does not exist. Does not exist. So this in particular will say that f is not continuous at 0. Okay. See, all other points, it's basically it's continuous, it's analytic, everything. So I'm claiming, so my claim, let me write that f satisfies the CR equations at z equals to 0. Indeed, it satisfies the CR equation on whole of C, but all on other part of the complex number, it's very easy because it's analytic. So only at z equals to 0, but it is not analytic at z equals to 0. Okay, and indeed, as I told, in fact, it is not continuous at z equals to 0. Okay. So if z equals to 0, it is not continuous. Okay. So see, here we cannot directly apply the del f by del z bar. Here, I'll just here we cannot apply directly that this is 0. We cannot, because we don't know that the z bar derivative exists or not. For example, see, for example, if you take fz equals to 1 by z, see, if you take the z bar derivative here, it's 0, but we don't know whether the z bar derivative exists, because that the z bar derivative is same as ux vy uy vx. Okay, but we don't know whether the partial derivative exists or not. So, for example, in this function, the partial derivative does not exist. So CR equal at, of course, at zero. So CR equation at 0 does not make sense. Okay. So similarly here, we don't, since it's 1 by z to the power 4, so we don't know whether it is the z bar derivative of this function exists or not. Okay. So that's why we cannot say directly that del f by del z bar equals to 0, because we don't know whether this expression makes sense or not. Of course, this does not have any z bar, so we can directly say. But since we don't know that the partial derivative exists, so we don't know. Therefore, we cannot directly apply. Okay, so this we cannot directly apply. Okay, so let's see. So it's a bit, it's not very difficult computation. See, I don't find any other method to check it. If you have any other method, you can suggest. I just found with, so what is my f? So f of z equals to e to the power minus 1 by z to the power 4. Okay. But what is this? This is e to the power minus 1 by x plus iy to the power 4. Okay. So, yeah. And this is nothing but, so I'll just do minus 1 by x minus iy to the power 4 by x square plus y square to the power 4. Okay, so let's just expand this. What is this? So x minus iy to the power 4 by x square plus y square to the, see, it's not a difficult expansion. So yeah, so what is this? So I just write down. So this is, if you write down, this is x4 plus y square minus 6. I guess it will be x4 plus y to the 4, I guess. Yeah, I have made some mistake. Yeah, this is x4 plus y4 minus 6x square y square, and then minus 4ixy times x square minus y square. I guess this, yeah. So this is divided by x square plus y square to the power 4. Okay. So therefore, what is my u? So uxy, this is basically e to the power minus x4 plus y4 minus. It looks bit ugly, but like it's not very difficult computation. So x square plus y square by 4. So this times cosine. So this will come cosine and sine. So this is cosine 4xy x. So this is just this by x square plus y square to the power 4. Okay. And similarly, v equals to the same thing with sine 4xy x square minus y square divided by x square plus y square to the power 4. Okay. Now you see, now it's just a matter of fact of multivariable calculus to check that limit. So what is ux? Ux equals to limit h tends to 0, u 0 plus h, because we are finding out at 0, 0, comma 0 minus u 0, 0 by h. Okay. And what is this? So of course the function value at 0 is 0, so u is 0. So this is uh comma 0 by h. Okay, but this value, if you'll take this, we can take the sequential idea an root I by n, bn, I both come to 0, but limit f of an not equals to f of bn. Yeah, but that says that the function is not continuous. Yeah, you are right. Whatever you told that says that the function is not continuous. The function not continuous does not imply that it will not satisfy the CR equation. This whatever you told, it just says that the function is not continuous. You are right. But what we are trying to prove is like the CR equation satisfies. So it means that ux at 0 and uy at 0, this is same as, so 0 means 0 0, at vy at 0 0, and vx at 0 0. So this is what, sorry, minus sign. So this is what currently we are trying to prove. And whatever Sariha suggested, that is basically will be helpful to, if we apply the polar form. Yes, we can apply the polar form, but as I told, see, the computation will be I guess with the same, like, because I was doing with the polar coordinates also, and this calculation was almost with similar difficulty. So I thought, since this is not very difficult, so I thought it's like better to like do with the direct, because it's just like very little computations. Okay, it's not like very fast computation. This is, see, even of course in exam, since you have all these three options false, so if the question is correct, then the correct option is this. Okay, so in exam, of course, you can directly say this is the correct option. But since we are in the method of learning, so it's better to compute and see what are the things. Okay, so this is what, this is equals to 0. Okay, okay, so that's fine. And similarly, if you'll find out u k 0k by k, that is also 0 limit k tends to 0. So these are not difficult. So yeah, so you can check this. This is just because we have already computed it. If you take h0, so this is basically 1. Okay, this is basically 1, and this will goes to 0. Because this is e to the power minus infinity. And this is what? Since x to the power 4 plus y to the power 4 by x to the power 8 is there. Okay. So this h tends to 0, this will go to infinity, but e to the power minus infinity will go to 0. Okay. And similarly for other thing. And for v, see, as xy tends to 0, this will goes to 0. So for v, nothing. So therefore, this satisfies the CR equation. So this satisfies the, very 20, yeah. So this satisfies CR equations. Okay. But as I told, this function is not continuous. It can be shown by like what Sari has suggested, to find out sequences, so that the f of a by an and bn like both converge to the same thing, but the limit are different. Okay. And you can also see there are a lot of ways to show that. So it's like e to the power minus 1 by z to the power 4, limit z tends to 0. Okay. But what is this? So you see, if I'll take x equals to 0 line, okay, then what is this? Limit y tends to 0, e to the power minus 1 by y to the power 4, which is equals to 0. But now if I'll take x equals to y line, then what is this? Limit x y, or x goes to 0, e to the power minus 1 by x plus ix to the power 4. Okay. And now what is this? This is what? This is x to the power 4, 1 plus I to the power 4. And what is 1 plus I to the power 4? This is 1 plus I square, is basically minus 2i. And if you do the square, so that's basically minus 4. So that's like minus 4. So this is coming, limit x tends to 0, e to the power minus 1 by x to the power 4, and minus 1 is there. So that's basically limit x tends to 0, e to the power 1 by x to the power 4. But that goes to infinity. Okay, as x tends to 0, this will go to infinity, and hence the limit does not exist. Okay, so this is a very nice example. So this is a nice example of a function. So this is a function which satisfies CR equations but not continuous even. Okay, and hence of course not analytic. Okay, so is this clear to everyone? Because see, like this is like we don't thought about, see, of course we know that if a function satisfies the CR equation it may not be analytic, but here it's even more weaker. It says that if a function not satisfies the CR equation it may not be even continuous. Okay, yeah, thank you. Okay, so let's proceed to the next problem. Yeah, so let's see this problem. Yeah, so any thought about this problem? That if T is the unit circle in the complex plane and D be the unit disk, so it's basically the interior region of this. I'll just take this. So this is mod Z equals to 1, that is T, and this is interior is D. And let R denote the set of all points Z0 in T for which there exists a holomorphic function f in an open neighborhood of Z0. So I take a Z0 here and such that Fz is analytic, such that this is okay. So this function, holomorphic function f in an open hover, this in this. Okay. So this function is analytic. So this is analytic. Although here it's written, so I'll just mark it here. So this function is analytic in the neighborhood of Z0. So it's basically mark a neighborhood. So in this neighborhood, if the function is analytic, then that Z0 is in R. And now the problem is, what is the intersection of R and Z, R and T? Like how many points are there in R which are there in T? Okay. So any guess about this problem? This is a very simple problem. This is not difficult. Yeah. So any guess? One. So all points of T. Okay. Okay. Let's see. Okay. What about others? Any guess? Okay, so let's see. So let's see which of the options are correct. So what it says, 2 and 3, infinitely many points of T and all points of T, right? So let's see. So let's see. 1 is true or 2 and 3 are true. Okay. So see, what is R? R is basically set of all F. So F has basically Z to the power 4n. N is 0 to infinity. Okay, F. So R is set of all Z not such that this function is analytic in a neighborhood of Z naught. Okay, yeah. But what is the radius? See, like what is the radius of convergence of this function? So if Fz equals to Z to the power 4n and equals to 0 to infinity, what is the radius of convergence of this function? So what is radius of convergence of F? What is that? That's basically 1. Because what? What is this? So this you can write summation n equals to 0 to infinity z to the power 4 to the n. So that's basically, this is same as n0 to infinity w to the n, where w equals to z to the power 4. And the radius of convergence of this is 1, and hence the radius of convergence of this is 1. Okay, so it means, it says that if mod z less than 1, then Fz is analytic. Okay. But if mod z is equals to 1, then this sum is not convergent. Not convergent. And hence, this implies that like at 1 and minus 1, I and minus I, all these 4 points, this function is not analytic. Therefore, for every z, so for every z such that mod z is less than 1, so R is what is R? The region R is Z such that mod Z is less than 1. So this is my region R. Okay. Now what was T? So T is set of all, yeah, such that mod z is equals to 1. Okay. Now you see that if I'll take a point here, okay, and now it says that in a neighborhood, so what is the, see, what is the property of R? The property of R is set of all z naught in T such that there exists a neighborhood u z naught, or it's there exists, or every, there exists a holomorphic function f in a neighborhood of this. Okay, so yeah, such that f is holomorphic in u z naught intersection D. So what is u z intersection D? It's this region, it's this interior region, this interior. Okay, this interior region. And clearly f is analytic at there. Okay, but these 4 points are the bad points. Okay, so these 4 points are the bad points. Therefore, there are infinitely many points of T where R and T are same, and all points of T except a finite. So because it misses only how many points? 4 points. So, okay. So, yeah. So, therefore, what is the correct option? See, even if you take this point, this has also the same property. Even if you take, although the radius of convergence is not at 1, it is not convergent, but it says that if I take this point, then also I can have the interior neighborhood, this, where function is analytic. In this, the function is analytic. Okay, so therefore what is the correct option? So these two are not correct. So what is the correct answer? All points of T, because it contains all points of T such that if you consider a neighborhood of Z naught, then U Z naught intersection with D, and that's the interior thing, and there F is analytic. Okay, so what is the correct option? So first is the, so is it clear to everyone? Yeah. So Chinu was right. Yeah, Viru. Yeah. So now you are also right. So is it clear to everyone? So here the confusing part is, see, you have this 4 points, so it was like very tempting to say that the option 2 and 3 are right, because these 4 points the function is not analytic. But if you read out the what is the set R, it says that R denotes the set of all points Z in T such that there exists a holomorphic function f in a neighborhood u z naught f z naught such that fz is analytic in u z naught intersection D. Okay, so yeah, so I guess this is the correct answer. Okay, so let's proceed to the next problem. Yeah, okay. So the last problem was clear to everyone, I guess. Okay, so let's see this. So consider the function fz, which is sine z by 1 minus cosine z and to the power m and to the power n. Then we need to see z equals to 0 is what? It's removable singularity, pole, or essential singularity, or what? Okay, so any guess about this problem? 1 and 2. 1 and 2. Yeah, so you are right. So let's see why. So see, if I write my g1z is what? It's basically sine z to the m, and g2z is what? It's 1 minus cosine z to the n. Okay. Now you see that z equals to 0 is a 0 of order 1 of sine z. Okay. Why order 1? Because the derivative is cosine z, and cosine z at z equals to 0 is not 0. So therefore z equals to 0 is a 0 of order 1 for sine z, for the function sine z. Okay. Okay, so this implies that z equals to 0 is a 0 of order, because you are taking the power m, so order m for g1z. Okay, so what is the order of 0 is m. Similarly, for g2, if you'll see, g2 0 is 0, not g2, let me write 1 minus cosine 0 is 0. And if I take the derivative of this, that's the sine z, and again at z equals to 0, that's 0. So that sine 0 is 0. And if you take the another derivative, that's not 0. So this implies that z equals to 0 is a 0 of order 2 for 1 minus cosine z. And therefore, the order, so z equals to 0 is a 0 of order 2n for gz. Okay. So now what we got, fz, or it's basically g2z. So fz was g1z by g2z. Okay. And z equals to 0 is, so order is basically m, and here the order is 2m. Okay. So now you see, so if m is bigger than equals to 2n. So if m is bigger than equals to 2n, so this implies that if I'll find out limit z tends to 0, fz, which is equals to limit z tends to 0, g1z by g2z, this exists. Okay. Okay. Because the order of 0 here, it's basically more than, so it's basically g1z is basically z to the power m kind of thing, and g2z is kind of z to the power 2n. And now if m is bigger than equals to 2n, if I'll find out limit z tends to 0, what is this limit will exist. Okay, so since here the order of 0 is bigger than the order of pole, or here order of 0 is bigger than equals to order of pole, so that's why this limit exists, and hence z equals to 0 is a removable singularity. So that's why the option 1 is correct. Now what is the second option, or let's analyze the m less than n. So if m is less than 2n, so this implies that it has a pole of, okay, so f has a pole at z equals to 0. Okay, because the numerator power is less than the denominator power. Okay, so therefore, if m is bigger than equals to 2n, we have a removable singularity, and if m is less than 2n, we have a pole. Okay, and no other types of singularity. So no essential singularity and no this. Okay, so the correct options are the first and second option. Okay, so is it clear to everyone? Okay, so I hope it is clear to everyone. Okay, let's proceed to the next problem. Yeah, yes. So it says that if f is an entire function such that it satisfies this inequality, then we need to find out what is the derivative of f at 0 and what is the second derivative of f at 0. Okay. So any thought about this problem? So what is the correct answer? Any thought? Okay. So let's see. It's again not very difficult. So you see. So I'll just write down a general problem instead of this, and then the yes. So first option is correct. You are saying. Okay, we'll see that where it went. Yeah. So let's see. So I'll just write down a general result and let's prove that. So if f is an entire function, f is an entire function bounded by a polynomial, bounded by a polynomial of degree m, then f is indeed a polynomial. Degree, degree. Okay, so this is a very important problem in general. See, whenever you have given an entire function which is bounded by some polynomial, then that function will indeed a polynomial. Question 6, why it misses only 4 points, there are other points. No, I'm not saying it misses the 4 points. So that was the thing I was emphasizing. See, um, where it went. Yeah, here. So here I'm not saying it misses the 4 point. I'm saying that the misses the 4 point is false. So see, like I'm saying that if you have this, if you take any point, if you take any point, let's say this point or this point or this point or this point or any point, if you have take any point, then you have in any neighborhood of z naught. So if this is my z naught, so in any neighborhood of z naught intersection with d, we have this, and then in this neighborhood, fz is analytic or holomorphic. Okay, and therefore, no, I'm saying in all points it will be same. So I'm saying that r is equals to t. R is equals to t. See, I was emphasizing that. See, usually what happens that if you like, it's very tempting that you will made a mistake that TR is equals to MT or R, sorry, or R equals to T minus 4 points, that plus minus 1 plus minus I. Like I'm saying that these options are very tempting that there is a fair chance that you will make a mistake by choosing this option that R is empty or R is T minus this 4 point. Why these 4 points? Because you will consider that, oh, radius of convergence is 1, so at z equals to plus minus 1 and plus minus I, this function is not analytic, and hence it will misses the 4 point. But t is basically this. T is basically mod z equals to 1. So it's basically whole lambda. It's not just only 4.1 minus 1 and plus minus 1 plus minus I. It misses, it's basically mod z is equals to 1 is this whole circle. This is the whole circle mod z equals to 1. So it won't message 4 point, it won't message any point. It's basically if you take any point, you have any neighborhood, then this function is analytic here. So I'm not saying that it will message the 4 point. Yeah, right. No, no, not only 4 points. Okay, right. Thanks. Okay. So yeah, so let's discuss this. So again, I'm emphasizing this here that whenever you have an entire function that is analytic on whole of C, so whenever you have an entire function and if it is bounded by a polynomial of degree m, then the function is itself a polynomial. Okay, and this is a very important problem. So its proof is also not very difficult. So let's quickly see a sketch of the proof. See, f is an entire function. So what does that mean? I can write the Taylor series expansion of f. Okay. So f z equals to um, summation an z to the power n, where n equals to 0 to infinity. And what is, see, whenever we have the entire function, then what is this? This is my, what is this? If you have the Taylor series expansion, then this is fn z naught or 0, basically I'm writing at 0 by n minus n plus 1 factorial times z to the n. Uh, See, the Schwarz lemma, I don't think so it will follow from the Schwarz lemma, because the Schwarz lemma only discusses in a unit disk. Okay, but we are not in a unit disk. We are discussing on whole of the C. Okay, Schwarz lemma only says that if fz is less than equals to lambda, mod of fz is less than equals to lambda mod z, then it has something. But like but that function is only analytic in the open unit disk. Okay, okay. So, but this is fairly easy. We just have to see. Sorry, got a call. Sorry, yeah, yeah. So yes. So what in order to show that f is a polynomial, what we need to show that what is f? F is basically a0 plus a1z plus a2z square plus dot 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 plus anz to the n plus the higher order term. So in order to show that f is a polynomial, we need to prove that after a certain point, these all are zero. Okay, then only we can say that the function is a polynomial. Okay, so so whenever in a Taylor series a function is polynomial, it means that we'll show that the derivative, because it means that fn at 0 is equals to 0 for n greater than some n naught. Okay, so after some point, the derivative at 0 is 0, because if this is true, then it means that this has only finitely many terms, and that means it is a polynomial. Okay, but that is very simple, because see, fz is bounded by a polynomial. Okay, so you can take any polynomial, but like let's take the m degree polynomial. Okay, just I'm taking, because the lower part I can always use I can always discard, or I can of course write down the whole term, but it's not a this thing. Okay, so fz is this. Okay, what you know from the Cauchy theorem, Cauchy's theorem. This says that Fn at Z naught is equals to something constant 2 pi IC, 1 by 2 pi IC, I guess, or n plus 1, or plus or minus, I don't remember actually, by 2 pi IC. This is Z by Z minus Z naught to the n. I guess this is right. Uh, this formula, I don't remember, but if it is false, you can let me know, because I guess if it is not correct, then it's like either this is n or this is n minus 1 or something like that. Okay, but it's something along this line. See, this is fz is, oh sorry, this is my fz. Yeah. So fz is bounded. So if I take here mod z equals to r, then what happened? This whole integral, or if I'll take this thing to the downside by n plus 1 factorial, then this integral, see, fz is bounded. So if I'll find out, so you have heard about the ML inequality, basically. ML inequality, which says that the integral of f is bounded by m times L, where m is the maximum value of fz and L is the basically the length of the curve. So here length is r. Okay, so if you will apply this ML inequality, then it says that this thing is bounded by, so this thing is bounded by mod z to the m by and times r to the r, and then and here you have another thing. But you see, yeah, so let me write down exactly mod zn, and here you have already 1 by z minus z naught, so it's basically 1 by mod z, or just write down 1 by r to the power n minus m. So this quantity is basically bound 2 pi I. So this quantity is bounded by 1 by r to the power n minus m. Okay. Now, as r tends to infinity, this will goes to, so if n is bigger than m, okay, m is the degree of the polynomial where f is bounded. Okay, so if n tends to infinity, this will go to 0. Okay, so it means that because r will be larger and larger, so as n tends to infinity, for any r as n tends to infinity, this will go to 0. And therefore, what will happen for every n bigger than m, this this will be 0. And we have only finitely many terms in the Taylor series expansion. And that will prove that the function is a polynomial. Okay, so here, so what we have proved is basically this, that if, so I'll just write down again this result, because this result is quite important result, and you'll see, like, with application to this, like, you can solve many problems. So it says that if fz is bounded by z to the m or any polynomial of degree m, and this says that f is a polynomial of degree m. Okay, now we are done. So it's just, so it means that what was the thing? So it was like z fz minus 1 plus e to the z is less than 1 plus, what was the thing? 1 plus mod z. Okay, now see, this 1 is of course fine, it's just constant. So it is bounded by mod z. And this is what? This is a polynomial, it's bounded by a polynomial. Z is a polynomial. And it's bounded by a degree 1 polynomial. So therefore, and f is an entire function, therefore this whole is an entire function. So therefore z times fz minus 1 plus e to the z is what? It's basically a naught plus a1z. It's a polynomial of degree 1. Okay, so we have this. Okay, now what I will do, I need to find out the derivative of f. So I'll just write fz is what? Fz is summation bn z to the power n equals to 0 to infinity. And I'll just, this is now just a bit of computation, nothing else. So z summation bn z to the n minus 1 plus e to the z equals to a0 plus a1z. Okay, and oh, of course, e to the power z also you have the power series expansion that says that 1 by n zn by n factorial n equals to 0 to infinity. Okay, so I'll just need to find out the n. So let's just find out. It's not again difficult. So n equals to 0 to infinity. Okay, so what is the constant term? So see, what is f prime 0? F prime 0 is because if I'll write down, let me write down again here, fz equals to f0 plus f prime 0 z plus f double prime 0 by 2 factorial z square plus f triple prime 0 by 3 factorial z cube plus dot dot dot. So what is the thing that we need to find out? We need to find out f prime 0 and f double prime 0. This. So this is my b1, this is my b0, this is my b1, and this is my b2. Okay, so I need to find out 2 factorial times b2 and b1. So I need to find out these two values. This is my f double prime 0 and this is my f prime 0. Okay, so is it clear? Till now, is this clear to everyone? It's a bit, a little bit computations are there, but the concept is clear. The main thing is that, of course, the computation you can always go and check. So yeah, please confirm me like if you have any doubt. Okay, fine. So right, then now I have to find out, just I have to need to find b1 and b2. Okay, so what is b1? Just find out, it's not too difficult. So let's see. So I'll just write down, I have done the computation, so I'll just write down here. Yeah, so if you write down what I'm getting is like I'm getting A0 plus, sorry, what happened? Hmm, crashes, so I don't know what happened. Just 1 second, I guess. Yeah, now is it visible? Let me see if it is visible because there was some problem happened. Yeah, let me just see if it is A0. Oh, so it is not. Okay, so it changes. Yeah, yeah. So my writing board got crashes. So just give me 1 minute. I'll just uh, do it again. It won't take much time. Yeah, I guess now, I guess it will be clear. Yeah, yes. So, yeah, where we were, yeah. So if you'll do the computation, so it's not very difficult. So you'll be getting A0 plus A1Z equals to summation n equals to 1 to infinity Bn minus 1 plus 1 by n factorial z to the n. And this will give me A0 equals to 0 and Bn equals to minus 1 by n plus 1 factorial. You can check this. It's I don't want to just go with the computation. You are like very good in computations, even better than me. So Bn is basically this. Okay. So what is my B0? B0 is fine. What is we need to find out what is B1 and yeah, B0 and B1 and B2. Okay, fine. So let's find out. And this is for n bigger than equals to 1. So what is my this is bigger than equals to 1. So what is my B1? The minus 1 by 2 factorial and B2 is minus 1 by 3 factorial. So what is this? This is minus 1 by 2 and this is minus 1 by 6. So what is f prime 0? It's B1, so minus 1 by 2. And f double prime 0 is B2, so that's, sorry, 2 times B2, so that's minus 1 by 3. Okay. So is it clear to everyone? Like I, of course, jumped a few steps here in the computation. So let me know if it is clear. Now, these computations are pretty straightforward. So that's why I jumped these computations. So if you have any problem, please let me know. We'll take a pause of 2 to 3 minutes. And if you have any problem in the like from problem one to problem, I guess this was eighth number. Yeah, if you have any problem from one to eight, then we'll see. And otherwise, we have a couple of more problems that we will be discussing. So yeah, so it's the right time to ask the doubts if you have any. So yeah, so is there any doubt, or we can proceed to the next problem? Because the February now this was the last problem in February 2022 next year. Okay, so now I have a couple of more problems, like I guess 3 or 4 problems, so that we will be discussing. If you do it without the expansion, see, without the expansion, we don't know what is f. See, of course, so we see what is, let me see if we can find out. So zfz minus 1 plus e to the z equals to a0 plus a1z. Okay. See, we don't know what is the f. So of course we can take the derivative. Let's take, yeah, you are right. We can take the derivative right from, but we don't know what is a0 and a1. Of course, we can find out, I guess we can find out the double derivative here. Oh, then fine. Then that's great. So let's see. So let's find out the first derivative. So if we'll find out the first derivative, we'll be getting z f prime z plus fz plus e to the z equals to a1. And if I'll do the second derivative, that will give me z f double prime z plus z, sorry, plus f prime z, and here we're getting plus 2f prime plus e to the z equals to 0. So if I'll do it, let's see. So if I'll put z equals to 0, so I'll be getting this will be 0. So f0 is equals to a1. Sorry, f0 plus 1 equals to a1. And if I'll put 0 here, then I'll be getting a0 is equals to 0. So a0 is already 0. If I'll put 0 it here. Okay, so a0 is already 0. f0 is basically right. Now what is f prime? So if I'll do the second equation, I'll be getting 2 f prime 0 plus 1 equal to 0. So this will give me right. So f prime 0 is minus 1 by 2. Yeah, so this I'm getting. And I guess if you'll take the third derivative here, so the third derivative I'll do, so I'll be getting z f triple prime z and plus I'll be getting here f triple prime, so f double prime and 2, so it's basically 3f double prime z plus e to the z equals to 0. And if I'll put z equals to 0, so this will go on. So f double prime 0 is basically minus 1 by 3. Yeah, you are right, Aviru. Thanks for this suggestion. Yeah, this is quite easy. Yeah, you're right. Yes. We put the, yeah, we don't need to put here also. Yeah, you are right. If you put z equals to 0 here, will give me the f prime 0. And if I take the next derivative and put z equals to 0, I'll be getting f double prime 0. Yeah, yeah, this is quite a lot easier than what I suggested. Yeah, thanks, Abiru, for this uh, suggestion. Yeah, yeah, you are right. And this is quite easier. Yeah. So, yeah. So, is there any doubt? Okay. So let's then proceed to the next problem. Yeah. So what is the radius of the convergence of the series z to the power n square? Yes. Yeah, Sarah. Sorry. Yeah. Okay. Yes. So what is the radius of the convergence of the series z to the power n square? So this is a very simple problem. So what is the radius of convergence of this series? Any thought? One. Right. Yes, you are right. One. Right. Yeah. One. Yeah. So let's prove that. That's not very difficult. So what? So basically, what we need to prove that this series converges. So the series converges if mod z is less than one, and diverges if mod z is bigger than one. Okay, this is what basically we need to prove that if mod z is less than one, then this series converges, and if mod z is bigger than one, then this series diverges. So these two will say that the radius of convergence is 1. Okay, fine. So let's see. See. So what is that? So mod z, if mod z is less than 1, then this implies mod z to the power n square is less than mod z. Okay, because mod z is less than 1, so power is less than 1, and you are like doing more powers and powers. So of course this quantity is lesser than this. Okay, so this implies, and we know that summation, or not this, sorry, summation mod z to the n. this. And we know that this series is convergent. This converges. This converges because mod z is less than 1. And hence by the comparison thing, the series this will also converge. Okay? Yeah. So now what if mod z is bigger than 1? Again the same thing. If mod z is bigger than 1, then mod z to the n square is bigger than mod z to the n. Okay, and now we know that this series diverges if mod z bigger than 1, like the series mod z to the n or the series z to the n. This diverges. And therefore, the series, this will also diverge. Okay. And these two things prove that if mod z is less than 1, the series is convergent. And if mod z is bigger than 1, the series is divergent. And hence the radius of convergence is equals to minus 1 to 1. Sorry, the radius of convergence is 1. Okay. Is it clear to everyone? And this is quite like quite a famous thing in the radius of convergence. And I guess there are a couple of shortcuts also to find out the radius of convergence. Okay, so if no doubt, so let's proceed to the next problem. Yeah, so it says that if f and g are two entire functions, that is analytic on whole of C, and gz is not equal to 0 for all z, and if if the absolute value of fz is less than equals to absolute value of gz, then which of the following is correct? Yeah, so any guess about this? Yeah, so any guess of this? 4. Right. So it's basically nothing but we'll use the Liouville's theorem, which says that an entire function, a bounded entire function is constant. A bounded entire function is constant. Okay. Okay. So this is what we are going to use in this problem, that whenever you have an entire function and if it is bounded, then we say that the function must be constant. Now you see that hz equals to fz by gz. You see that g is not 0 for all of c, and f and g both are analytic or entire. So therefore, g gz is not equal to 0 for every z. So this implies h is an entire function. Entire function. Okay, so this says that h is an entire function. Okay. Now, whether h is bounded? Yes, h is bounded. Why? Because of this condition. So, mod of hz is equals to mod of fz by mod of gz, which is bounded by 1. So, therefore, h is an entire function bounded by 1, and this proves that h is constant. H is constant, and therefore hz equals to c for every z, and then this proves that fz equals to c times gz for some c, and therefore this option is correct. Is it clear to everyone? Okay, yeah, okay, so let's proceed to the next problem. Yeah, so problem number 11. It says that if f is an entire function and f of 1 by n square equals to f of I by n, then which of the following are necessarily true? That f is a constant function, f0 equals to 0, fz square equals to f of minus z, or such an entire function does not exist. So yeah. So what do you think about this problem? So I'll give 2 to 3 minutes to think about this. If you have an answer, you can tell. The previous one is MCQ or MSQ. I guess it's it. See, the option is like I just created some options randomly. So this is the only correct option. So what even it's MCQ or MSQ, this is the only because F0 is 0. This need not be true always. F is a constant function, this is also not true always. And fz not equals to 0 for all z in C, that's also not true always. So that's why these three options are false. And this is the only correct option. So yeah, so it's either the MCQ or MSQ. The correct answer will be the fourth answer, the fourth option. Okay, Manohan? Even in this also, I guess in this problem, this is also the multi-selective. You can say this is also multi-selective question. So in this problem also more than one options can be true. F can be constant. Yeah, it can be constant, but it says that see when I'm saying then it means that I'm asking that like for previous question. Yeah. Yeah, for problem number 10, I guess you are talking about. Yes, see, it can be constant, but what I am saying that it is given that f is a constant function, but f need not be a constant function. I am saying that f need not be a constant function. It says that then f is a constant function. This is not a correct statement. Then f is a constant function. This is not a correct statement. Of course, f can be a constant function, but f is a constant function, not a correct statement. Or the correct problem would be like then which of the following is or are necessarily true, are necessarily true. Okay, which of the following are necessarily true, not always true, right? Yeah. Yes. So yeah, so what about this problem number 11, that f is an entire function, it satisfies this. So the 1 and 2, f is a constant function and f0 equals to 0. Okay. Okay. So you are saying that f0 is a constant function and at 0 it's 0. Okay, let's see. So again, see, we have a sequence involved. So the what is the main ingredient to like which deals with the sequences is the identity function. Okay. So see, if I'll take fz square equals to, or if I'll take my gz equals to f of z square minus f of iz. Okay, then what is g of 1 by n? G of 1 by n is f of 1 by n square minus f of I by n. That's 0. Okay, and therefore, and if I have s equals to 1 by n such that n is in n, then this has a limit point 0 and which is in C, and therefore g is identically 0 function. And therefore, what is f? Fz square equals to f of Iz. Okay, so we have this. Okay, right. So, okay, now I need to see whether this condition implies that whether f is a constant function or not. Okay, so let's see. So first of all, let's see whether this is correct or not. So of course, fz square is equal to f of iz, but whether that is correct. So if I'll take, right, so you can write this as minus of z square equals to f of z. See, if I this is equivalent to this. Why? Because if I'll put iz, then what is this? This is, if I'll put iz, then that's z square equals to f of iz. So this is true, but this does not imply that f of z square equals to f of minus z. Because if you'll put z equals to minus z, what we will be getting here, that f of minus z equals to f of minus z square. So so therefore this option is of course false. Okay. Okay, such an entire function does not exist. We don't know yet. So let's see. And we from here we can only see that f0 equals to f of 0. We don't know whether it's 0 or not. So let's see now. F of z square equals to f of iz. Okay. If I'll find out the maximum value of f on mod z less than equals to 4. Is it same as maximum value of f on mod z less than equals to 2? Are these two maximum same? Because see, what we are doing, maximum of f on z mod z less than equals to 4 and maximum of f mod z or mod z less than equals to 2. Because these two are same. Okay, because we have having mod z square and iz. Okay, so it means that f have a maximum value on this and also this. But this says that if f, so if I'll considering, if take f, if I'll restrict f on mod z equals to 4, then this says that f has a maximum value inside. Okay, on inside f has a maximum value. And this from the maximum modulus principle says that f is a constant function. Okay, what is maximum modulus principle? It says that if the maximum of a function lies inside the boundary or inside the domain, so if f is analytic on omega and the maximum lies inside here at z naught, okay, then f is a constant function. So the maximum cannot lie inside the domain. Okay, so therefore f is a constant function. And this says that if I restrict f on mod z equals to 4 or mod z less than equals to 4, then the maximum lies also inside the domain. And hence, this says that f is a constant function. So this proves the first thing. So this of course not true. Okay, so f is a constant function. Okay. Now, why f0 equals to 0? So, do you have any thought like if f0 is always 0? Because I can take f0, I can take f as f equals to 1. If I take f equals to 1, is it satisfy the first condition? Chinu and Sariha? If I take f equals by minimum modulus. No, it's a maximum because the maximum of f lies inside the domain. Minimum says that for minimum f has to be non-zero. Then we'll apply the maximum modulo principle by 1 of f. Okay. The maximum modulus principle says that on the maximum cannot be in the interior. It has to be on the boundary. But here maximum is on the boundary as well as in the interior. And therefore f has to be constant by the maximum modulus principle, not the minimum modulus. Minimum modulus, in order to apply the minimum modulus, we have to ensure that f is non-zero function. Then only what we do, we apply the maximum modulus on 1 by f, and that will give me the minimum modulus. And here we are applying to the maximum modulus principle. Yeah, but see, if I'll take f equals to 1, just take f equals to 1. If I'll take f to be 1, does it satisfy this condition, Aviru? If you, of course, if f not 0, then the minimum on the boundary but inside the interior. Yeah, I gave you a function, f equals to 1. Is it satisfying the above condition? What is f of 1 by n square? It's 1. And what is f of I by n? It's 1. And it satisfies the condition. But f of 0 is not 0. And therefore, f of 0 need not be equals to 0. Yeah. So it means that f of 0 need not be equals to 0. Okay. So this is false. Yeah. And this is correct. Okay. So yeah. So this proves this thing. Let's let's see this problem. So if you have any doubt in the earlier problem, please let me know. If you have any doubt in the earlier problem, so here we have applied two things. The first is the identity theorem, and the second is the maximum modulus principle. Okay, and there are a lot of ways to prove that f has to be constant. This is just one way. Okay, so yeah, if suppose f is an entire function and fz equals to f of 1 by z, then what can you say about f? This is also multi-selective. This is also multi-selective. So Abhirup, is it clear, the last problem? Okay. Yeah. So what about this? Okay. So suppose f is an entire function which satisfies that f of z equals to f of 1 by z. Then is it a bounded function? Is it a constant function? F is a non-constant function, or f is a bounded on mod z greater than r. So think it's just one or two line thinking. Just think a little bit. I'll wait for 1 or 2 minutes. Please repeat option 2 of question 11. Okay, I'll repeat after we finish the question 12. I'll again go to the question that option 2 in of the previous problem. Yeah. So suppose f is an entire function and fz equals to f of 1 by z. And the hint is that use the Lively's theorem that an entire bounded function is constant. This is the hint. So it means that we need to prove that f is a bounded function. So see, bounded means what? See, if so, f is bounded means whole on complex. It means that for every z, like f, so there exists some m such that f of z less than equals to m. This is the bounded. Okay. So if I'll take mod z equals to r or mod z less than r, let's take mod z less than equals to r. Sorry, r. Is f bounded on this region? Ah, yes, yes, of course. Oh, z in c minus 0. Right, you are right. Z belongs to c minus 0. Yes. Thanks. Yeah, the equality is there for all z except 0. You are right. Yes. Yeah. So if I'll take mod z less than equals to R, then is F bounded? Yes, F is bounded. So F is bounded on mod z less than equals to R. Why? Because F is an analytic function and hence continuous, and continuous function on a compact set is compact, and hence F is bounded on mod z less than equals to R. Fine. Acha. Whether F is bounded on mod z greater than R, is it true that F is bounded on mod z greater than R? And for this, we need to use this condition that f of z equals to f of 1 by z. Okay. See, f of z equals to f of 1 by z. So whatever the value of mod z bigger than r, so with this, since the value is same, so see, f of 1 by z, this function is bounded. So if I write this function is bounded on mod z bigger than r. And this proves that on mod z greater than r, fz is bounded. This is also true, this is also true. And therefore, combining these two, f is bounded on pole C. Now we got a bounded function. So this implies that, and f was an entire function, so entire bounded implies constant. So this implies f is a constant function. So is it clear to everyone that how I prove the boundedness here? Because we are given with mod z and z and 1 by z. No, so that's why see what I am saying, that a bounded and entire function is constant. Sin z is not constant. So f is an entire function and it is bounded, and hence it has to be constant. See, Liebniz theorem does not say this, whatever the theorem you have cited, Liebniz theorem, it just say, this is what I am saying, that the theorem, it says that a bounded entire function is constant. So since f is bounded and entire, it has to be constant. Okay. Or in other word, a non-constant entire function is unbounded. A non-constant entire function is unbounded. Okay. So since here we have proved that f is bounded and it is given already that f is constant. So bounded plus, sorry, it is already given that f is an entire function. So bounded plus entire implies that f is a constant function. Oh, less than equals to r. Yeah, you see. Sorry, what I did. Just a minute. Press. Add a new page here. Yes. So see, f is an entire function. Fine. This is an entire function. And see where we are discussing the boundedness. We are discussing the boundedness on mod z less than equals to r. Okay. Is this a compact set? This is a compact set. F is a continuous function. F is continuous. So on a compact set, the continuous map sends a compact set to a compact set. So image f of z on this. So if I'll write B, F of B is compact. F of B is compact. And this implies F is bounded. See, I am not saying that it is bounded on whole of C. I am saying it is bounded on a compact ball. I am not saying that F is bounded on whole of this C. For example, whatever the example you gave, sin z, sin z is bounded on mod z less than R, mod z less than equal to R. Sin z is bounded in this. Even any analytic function on a compact set is bounded, or any entire function on a compact set is bounded, because that's not a property of an entire function, that's a property of a continuous function, that it sends a compact set to a compact set. So whenever we have a compact set, the image will be compact and hence it will be bounded. Yeah, but I'm not saying that sin z is bounded on whole of C. Okay, so the first line that I wrote here, that f is bounded on mod z R. This is because is f is a continuous function, and mod z less than R, this is compact set. Okay, so is it clear, Abhiru, that why we are concluding that f is bounded in mod z less than equals to R? Yes. Okay, fine. So this proves that f is a bounded function, f is a constant function, and f is bounded on mod z greater than R. Okay, so is it clear to everyone? Okay, so let's see. Uh, so I guess Chinu had some doubt in problem 11, option 2. Okay, let's see. See, okay. So it says that we have already proved f is a constant function. It says that at 0, the value is 0. What I am taking, f z equals to 1. You take any constant function other than 0. Okay. So is f, first thing, f is an entire function. So first thing, f is an entire function. So let f be an entire function. This is true. Okay. Now second is, f has to satisfy this, that 1 by n square equals to f of I by n. So what is f of 1 by n square? F of 1 by n square is 1. And this is what? This is f of I by n. Because f is a constant function, so whatever value you take, it has to be same. So it satisfies this also. Therefore, fz equals to 1 is a correct choice. Even fz equals to 2 is also a correct choice. Fz equals to root 2 is also a correct choice. Whatever constant function you will take, it is a correct choice. So f0 equals to 0 need not be true. Okay, so this is true only if we take f is 0. Of course, this is one possibility, but this is not always true. Okay, so is it clear, Chino? Okay, so I hope it is clear. Yeah, okay, thanks. Okay, so this completes the list of problem that I had. So yeah, so if you have any doubt till now, you can ask, and then yeah, and what I'm planning to take some like problem sessions, like practice problem sessions on linear algebra, real analysis, complex analysis, abstract algebra, some practice sessions. So we will quickly recall some of the important results probably in the next session. So in the next session, the either I will do what is this abstract algebra, or what we can do we will recall some of the important results, some of the important results, and we'll do some problem based on that. Based on that. So what do you suggest? So we should do the first one or the second one? Yeah, so like what do you suggest? Okay, okay. And what about others? So what do you think? Which will be fine? Second, okay, okay. So yeah, okay. So the majority says the recall some of the results and then we'll do problem based on that. Okay, so I'll try to do that. We'll I'll try to like gather some important results and like you guys can also like if you guys are on the WhatsApp group, if you have some nice result that you think that result is useful, so you can share on the WhatsApp group because it may happen that I might not able to collect all the important results. Okay, so if you think that okay this if you are reading something and if you think that that result might be an important result, so you can share on the WhatsApp group. What I will do, I will try to like combine all the results and make some problems like two or three problems or more of each result, and then we will try to do that. Okay, is it fine? It's like because then like you will also think, oh, this result is an important result, so let's write down and click a picture and send it to the group so that everybody will be like familiar with that. Oh, this result is a very good result. Example f equals to 1 in that problem, we considering max of the sets. Likewise, can we consider min of those sets and apply the minimum modulus principle? So in this which problem? Oh, the earlier problem. Okay, this. Yeah, see, Aviru, uh, even if what you told, if f is a non-zero function, then you can do the you can consider 1 by f and apply the minimum modulus principle. Minimum modulus principle will again with the same concept will give you that f is a constant function. So 1 by f is a constant function. But that is fine. We are not getting any contradiction. See, we should, if we get a contradiction, then we could have told that, oh, since we got a contradiction, therefore f has to be a zero function. But since we are not getting any contradiction, whatever you are telling is just right. If you take 1 by f and apply the maximum modulus, or on f apply the minimum modulo principle by assuming that f is not zero, either of they will say that f or 1 by f is constant. But that is not giving any contradiction to anything because f is constant. It is we already got that f is constant. Okay, yeah, thanks. So yeah, so whatever I propose, is it okay for everyone? Because as I told, I might not get enough time also to collect all the like nice results or because it will always be good if like all will be involved to have some good results that is important for NET, GATE or any other exams. Okay, so I suggest that you also help me to gather those results. In case if you are reading something and find some good results, or you think that is a good result, just send that on the group, and we will see that if it is a nice result to have it, we will include that, and I'll try to set some problems on the basis of that. Because I might not be, see, of course, I'll not be available on next to next week because I'll out of the city. Okay, so we'll try to like we will have our session on again next Sunday. So next Sunday we'll meet again. Saturday I'll not be there, so Saturday again we cannot meet. So Sunday we'll be meeting. So probably don't know the date. So I guess 21. Okay. So we'll meet on 21 and we will discuss some important results and problem based on that. Okay. So goodbye and thank you for your patience. We'll meet again on the next Sunday. Okay. So let's end the session today.